Last lecture, which means yesterday's lecture, we had seen this particular slide here for a common source amplifier with a resistive load here, RD. And we had seen that if you look at the gain of this particular amplifier, one of the ways of increasing the gain is that according to this expression, if you keep the size of the MOSFET fixed and the voltage swing is also fixed here, then one of the ways of increasing the gain, as you can see from this particular expression here, is that you reduce the drain to source current. And this is what you can see here, that for 100 microamperes you have a gain of 4.4. And note that as you reduce the current, IDSQ, what you do is you simultaneously increase RD as well. Okay, and so what you can see here is that gain is pretty small when currents are large, but as the current reduces here, the gain steadily builds up, and one can get reasonable amounts of gain here, 50 or 60 here that you can see, if one goes to a current which is low enough. But the price that one has to pay is that the resistance that one has to use is also pretty large here. 3 mega ohm resistor here. And the reason why I'm saying is this is a costly thing is because large resistors are difficult to make on chip. They take up a lot more area. And therefore, if you want to build up high gain, then you have to look for an element here which has a high small signal resistance, but at the same time doesn't occupy large amounts of area. And we had seen earlier that a good replacement for this particular resistor is a transistor here. So we move then to a common source amplifier with an active load. When we replace the resistor by a transistor, then this particular load is an active element, and so we have a common source amplifier with an active load here. And one of the ways in which you could do it is simply replace RD by an NMOS transistor here. And if you recall, we had seen for bipolar also, that if this is a BJT here and you add NPN here and you add an NPN here, you don't get large gain. You don't get large gain. This is not the way to build a common source amplifier with an active load if you want a large gain here. I'm not going to go into the details here. You can easily replace each transistor by its model here, small signal model. This is for M1 and this is for M2 here. And then a couple of simplifications will tell you that the gain of this particular amplifier, you can look at the derivation and an approximation here. The gain of this amplifier is basically dependent on the ratio of the sizes of M1 and M2. The ratio of the size of M1 and M2. So if you assume that the channel length is the same for both the MOSFETs, then it is W1 by W2. 1 plus eta is a small factor. Maybe this whole thing is around 1.45 or 1.5 here. So which means that this particular stage will not give you sufficient gain, because note that even if I make the size of M1 100 times larger than M2, then all that I will get is a factor of 10. And 10 divided by 1 plus eta here, so it will be less than something around 8 or 7 or something of that sort here. So I'll get a small gain. And therefore, this particular amplifier, where you have an NMOS, which is a driver, and you have a load, which is also an NMOS, you don't end up getting large amounts of gain. So from that point of view, it's not a very useful stage here. But from another angle, this can be fairly useful, because if you note the expression for gain, the gain is very stable. The gain depends only on the ratio of the sizes of the two transistors here. So it's very, very stable, which means what? It will not depend on the supply voltage. It will not depend on temperature. And therefore, this is giving you a gain, low value of gain, but an extremely stable gain. So if you're looking for, in your application, moderate or low, maybe 5 or 6 or that kind of a gain, this can prove to be a useful stage. Now, as I said, we had seen earlier, the reason why this is low gain is, note that what happens is, for voltage gain, what is important is, what is the net resistance at this particular stage? Okay, net resistance at this particular stage. So if I look at this particular node and I ask what is the net resistance at that particular node, then if you look down here, what you see is the resistance. You're looking into the drain of M1 And when you look into the drain of M1 here, when you look into the drain of M1, what do you see? R01. You see a large resistance, okay, which is fine. But then when you are at this particular node, the net resistance is resistance looking down and resistance looking up. That's the other resistor here. And here you look into the source. And when you look into the source of a transistor, and it's something similar to looking into the emitter of a bipolar transistor, and the resistance is small. Okay, and we'll show you later on that as you look into the source, the resistance is small. So the net resistance at this particular node is a large resistance R01 in parallel with a small resistance of M2 because you're looking into the source of M2. And therefore the net resistance at this particular node becomes small. And if the resistance at this particular node is small, the gain developed at that particular node becomes small as well. Okay, which you will see in more detail a little later on. So the idea is that if you want to build large gain, then you don't use an NMOS, you use a PMOS transistor here. And this one then we can analyze in a similar manner. We replace M1 by a small signal model here. We replace M2 by a small signal model as well. And so this is the, note the directions here. The directions of the these dependent current sources are always from drain to source. Drain to source here. This is the source end here. And gate, of course, is ground. And so this is the model for M2. And note, in a PMOS, we'll always assume that the source is tied to the body. Okay, because each PMOS node that can be made in a separate well. And so it doesn't show here, but the source here is, the body here is tied to the source. So this particular current source becomes 0. So you can ignore it and you are left with this particular one over here. Okay. All right. So if you look at this particular one also, you note that the gate is ground and you know that the source is also a small signal ground here. So VGS2 is also 0. VGS2 is also 0. So both these current sources basically drop out. They're all open circuit, 0 current, and you are left with only R02. And which is what I was saying, that this M2 in a small signal equivalent circuit simply acts as a resistor, as you can see here. It just boils down to a single resistor R02. And it's a large value of resistor, and that is what our goal was. Our goal was to replace RD here by a large resistor without occupying too much area, and this is what you end up getting. So you get a large resistor R02 and due to M2 here. And the M1, this is this part of the circuit here. So you can see now easily the gain that you will develop is this current will pass through a parallel combination here, and the gain that you get is minus GM1 R01 parallel R02. And because R01 and R02 are large quantities, and therefore you are able to build up reasonable or high gain at this particular node here. Okay. Now, if you look at this particular circuit, has several messages for us. As I said, if you look at this one, I was just mentioning a little while ago that the net gain that you develop at this particular node that you see here is dependent on what the net gain that you are building. There's a current source here, GM1 VS, which is coming from the applied voltage here. That's the current source. The current source flows through a parallel combination of net resistance at this particular node. The net resistance at this particular node is what? Even without looking at this particular circuit, you know that if you look down, you see R01. If you see up, now when you see up here, you're looking into the drain. And when you look into the drain, you see again R0 of that particular transistor here. So you have R0 of M2 and you have R0 of M1, and both of them are coming in parallel, and therefore you have a large resistance here. All right. So it also tells you, okay, all right. So this is then what you are seeing here is that you have a current source which goes through a parallel combination of net resistance at this particular node. Okay. All right. So let's take an example here. So we have M1 here, M2 here. Both are of size 2 by 1. They're biased at some voltage 1.5 here, which gives us a IDSQ of 25 microamperes here. And we are assuming here that the drain, see, it's difficult to calculate drain to source voltage here. Because if note that both the transistors are biased in saturation region. And therefore, this is acting like a current source, and this is acting like a current source as well. And it's not obvious how to calculate the drain to source voltage in this particular case. Normally what happens is that you take this particular stage, embed it in a multi-stage amplifier, and you put a negative feedback loop which decides, which forces this particular value to an appropriate level here. So I'll not go into the details, maybe we'll see it later on here. So right now we are assuming that this particular stage is biased right in the middle here, 3.30 here, so it's biased at around 1.65. So we are sort of assuming. There's no guarantee that this particular one will give it this particular value, but as I said, if you put it in a negative feedback loop, you can force this particular value to around this 1.65 here. But let's not bother about this for a moment here. So this is the current then, and for this current we can calculate GM of this transistor, GM of this transistor, R0 and R0P. The values are given here, and then AV turns out to be GMN as GMN means of this transistor, R0N parallel R0P, R0N here, R0P here. Gain turns out to be 200 here, and R0, the net output resistance, is a parallel combination here, which turns out to be 2 mega ohm. All right, so we see that you can note that these are very small transistors, 2 by 1 here and 2 by 1 here. So without requiring a very large resistor, we've been able to obtain very high values of gain here. Okay, so that's the advantage of a common source amplifier with an active load. The price, of course, that you're paying is that the output resistance is very high. That's the only way you can build up gain. If you go back into this particular thing here, if you see that this current GM1 VS is fixed, so the only way you can get high gain is by building a high resistance at this particular node. And so the price that you always have to pay for a large gain is that the output resistance. Output resistance is also resistance looking from here, and output resistance is nothing but the parallel combination. So that's the price that you have to pay here, output resistance being very large here. Let's come back. So we'll repeat the calculations. So gain, output resistance we have seen. Swing, as usual, we have this particular diagram here. Now, of course, we have to bother about that both the transistors should not enter into triode region, and therefore we have a band here which says that your transistor should not enter into triode region for M1, and the transistor M2 should not enter into triode region here. So these bands are saturation voltages of M2 and saturation voltage of M1, and therefore one of the limits on swing will come that this positive part here should not can at the most touch this particular region here, and negative part can touch only this particular region here. So we get these two limits. One of the limits is, as you can see here, VDD. This is the DC value here. So VDD minus V0 DC minus VSAT P. So this is coming from here. And the other one is coming from here, V0 DC, whatever is the DC value here, minus VSS minus VSAT N here. So you're getting two limits, one from this side and one from this side. And these two limits ensure that the transistor does not enter into triode region here. The other limit will come from harmonic distortion, and harmonic distortion limit we saw in the last lecture is IDSQ, the net resistance at this particular node, R0P parallel R0N multiplied by HD2 by 12.5. Okay. Earlier, if you recall, our expression had IDSQ times RD here because the net resistance was RD parallel R0 here, and we were neglecting R0. Now we can't neglect either of these resistors here, so we put R0P parallel R0N multiplied by HD2 by 12.5. So these are the three limits here. Whichever one is smaller will determine the output voltage swing. And I'll just show you in a minute through calculations that now what you will find, that note that this R0P and R0N are very large. So this limit turns out to be very large here and plays less of a role. Harmonic distortion does not bother as much for a common source amplifier with an active load because of this large value here. So let me show you some calculations. So as I said, this is 3.3, this is 0, and we are assuming that is biased right in the middle at 1.65. So the first limit is 3.3 minus 1.65 V0 DC here, minus saturation voltage of 0.5. How do I get saturation voltage of 0.5? If you note, the VGS for this transistor is 1.5 and VGS minus VT is 0.5. So something similar here. For this transistor also, VSG is also 1.5 and 1.5 minus 1 gives us a saturation voltage of 0.5 here. So this limit is 1.15. This limit is also 1.15. Both are equal. Since we have bias in the middle, transistors are all have similar properties. So both these limits are the same. Let me put in the values here. For 5% is harmonic distortion. For the current 25 microamperes, if I put in, this value comes out to be 20 volts for 5%. Okay, which means that if you allow 5% harmonic distortion, theoretically, it can go as large as 20 volts here. So basically saying that this is not does not determine the voltage swing anymore. If I put 1% here, then of course it will go down to 4 volts here. Still is larger. Okay. So what it says is harmonic distortion will not bother you as much in this particular case. And what will determine the swing then are these two limits. And therefore, if you bias it right in the middle, then you'll get a swing which is half the supply voltage. 3.3 minus 1.65 is 1.65, half the supply voltage minus the saturation drop, whatever is the saturation drop. You can get that high a voltage swing here. And now here you can see ideally the maximum swing that I can get is 3.3 minus 1.65 is 1.65. And if you make this very small here, saturation voltage, then the maximum swing that you can get is half the supply voltage. But to get that, you have to make the saturation voltage very small. And if you recall, the saturation voltage is inversely proportional to the size of the MOSFET. And therefore, if you want a very large swing, you'll have to make the saturation voltage very small, and that would require you to make the sizes very large. You'll have to make it, 50 by 1 or 100 by 1. Then only the saturation voltages will become small, and you'll get larger swing there. So the price that you will end up paying for very good swing is large sizes of the transistors here. And large sizes, besides occupying more area, what will happen is large sizes will have large capacitances. They'll have large capacitances, so your frequency response will suffer. Okay, so these things, as you can see here, gain, output resistance, swing, frequency response, they're all coupled to each other because they're all depending on the same factors. The factors that are under my control are the current and the sizes of the transistors. And they will affect your gain, they will affect your output resistance, they'll affect all the parameters. So as you try to improve one, obviously the other one most likely will get compromised. So this harmonic distortion then is less of a problem. All right, frequency response. As usual in frequency response, as I was explaining in the last lecture, what you do is in the circuit you identify the nodes here. This is our method for calculating frequency response, sum of the time constants. And what you do is you identify the nodes. So we have two nodes here, one node here and one node here. The other two are trivial nodes at fixed voltage, so we won't bother here, these two nodes. And at each node, you identify the net resistance at that particular node, the net capacitance at that particular node, multiply them together, and then sum up. That's all you have to do. So let's see, at this particular node, the net resistance, please remember that when we talk about net resistance and net capacitance, it's always between that particular node and small signal ground. Okay, so when I say net resistance at this particular node, it is between this node and small signal ground here. And so one resistance is from looking down, which is R0N. And the other resistance, this is also small signal ground. The other resistance is looking up here. This is R0P here. And note that both resistances come in parallel. It is between this node and ground, and this is also between, which is also ground, small signal ground here. So you get net resistance at this particular node here, which is output resistance here. And net capacitance here, now you have to recall net capacitances will come from all the transistors which are attached to this particular node here. So first you start looking at the transistor, let's say N-type, and at this particular node, what you have is, this is drain node, and there'll always be a capacitance between drain and body. That's the first one, drain to body capacitance. The other one is between drain and gate, and you apply Miller's theorem, and you gate and drain, so it becomes 1 minus 1 by AV. So that's the net capacitance that comes from the NMOS here. Then you go to PMOS, and the net capacitance that comes from PMOS is the gate to drain of PMOS here, gate to drain of PMOS. Note that there's no Miller's effect here, because the gate is what? Gate is ground. small signal ground here. Okay, so gate is small signal ground. So it's simply the capacitance that comes from here is CGDP here. Okay, and the other capacitance that comes is drain to body of the PMOS here. So note there will be a capacitance between drain and body. Body is connected to the source, and source is small signal ground. So that capacitance is also between this particular node and ground. So this is the net capacitance at that particular node here. So you calculate all these capacitances, multiply them together, you get this time constant here. Coming back to this particular node, the net resistance at this particular node again is resistance looking right, which is infinite, resistance looking left, which is RS. So the net resistance becomes RS parallel infinite resistance, which is RS here. And the net capacitance at this particular node, you can see here, this is CGS of this particular transistor. That's the first one. And CGD here, the gate to drain gets multiplied by 1 minus AV, the gain of this stage here. So you get the net capacitance of this particular node, and you multiply them together, and you'll get the values that you want here. So as an example, CGSN, I've given you all the values here. 4 femtofarads. CGD is smaller, 1 order smaller here. Drain to bodies are comparable. So note the net capacitance that comes out is C1, 84.4 femtofarad. C2 is 8.8 femtofarad here. And then, of course, one can plug it in and calculate the 3 dB frequency here. Important point to note here is that C1 has become much larger, and the reason for this is basically this one here. CGD, note that CGD is 0.4 femtofarad, but the gain of my amplifier is 200. So this 0.4 getting multiplied by 200, and that is what is contributing to almost 80 femtofarad. So very large amounts of capacitance is appearing at this particular node, all because of this Miller multiplication. And so that's a major problem that needs to be solved. And 3 dB frequency then is 9 megahertz for RS equal to 0. If RS is 0, then of course all C1 doesn't matter anymore. On the other hand, if RS is there, C1 matters a lot, and the 3 dB frequency drops from 9 to 1.56 megahertz here. Okay. So one of the problems that needs to be addressed is that the gain of this particular amplifier is large, which is good, but as a consequence of the gain, the Miller's effect causes a large capacitance to appear here. And anytime you're driving this amplifier through a resistive, your source has a resistance here, then you'll get this large time constant here. You'll get a large time constant because of this, and 3 dB frequency will become very small. So that's a drawback, that Miller's effect is very, very prominent in this particular amplifier. So this is a comparison of the two amplifier stages here. This is a common source amplifier with a resistive load, and this is a common source amplifier with an active load here. And you can compare the two. Both of them are biased at 25 microamperes. And you can compare the two. Gain here was 8. Both sizes are the same, 2 by 1 here. Here we have chosen 80K. So gain is 200, gain is 8 here. Swing, you can see here, swing, harmonic distortion doesn't bother. Swing is also better here. And of course, price that you have to pay for large gain is that 3 dB frequency here, even for RS equal to 0, is only 9 megahertz, while 3 dB frequency here was 0.45 gigahertz. So when you build up large gain, what you end up doing is you build up large resistance at this particular node, and large resistance, as you know, increases the time constant and causes the 3 dB frequency to drop here. So you can see a comparison here. So this stage is a very popular stage. Anytime in a MOS amplifier, you want to have large gain. So this is the one that is prominently used. But a problem with this particular stage, as you can see, is that it suffers from this Miller's effect. Miller's effect, which causes the gain of 3 dB frequency to drop a lot. Okay. Now, so the amplifier, as I was mentioning here, in all these amplifiers, the gain depends on the net resistance at this particular node. Resistance looking down, as you can see, R01. Resistance looking up is R02. So if you want a larger gain, right, what should you do? What should your strategy be? Say I'm getting a gain of 200. I want 300 or 400. What should I do? large gain. What are the things under your control? Suppose I don't want to touch this GM1 here. One way is, of course, you try to increase the transconductance by increasing the size of M1 and, the other ways that are there. But suppose this factor is fixed, you don't want to touch this for a moment, then the only thing that you're left with is these two resistances. So, and these two resistances are resistance associated with M1 and resistance associated with M2. Can I increase this resistance here? Suppose I replace M2. I take M2 out. Can I increase M2, resistance associated with M2? Which means that I'm going to take this particular element out and replace it by another element. Maybe a transistor. How about this one? Focus on this particular node here. Again, the gain is being developed here. Resistance looking down is again R01. When you look up, what do you see? You see a stack of two transistors. You see a stack of two transistors. Now, when you look up and you calculate the resistance due to M2 and M3 in series, that resistance, if you do the small signal calculation, will become much larger. Will become very large. And therefore, what will happen is, effectively what you have done is, this R02, resistance looking up, becomes much, much larger than R01. And therefore, your gain will become primarily equal to GM1 times R01. And if R01 and R02 are the same, let's say, then effectively what you've done is you've doubled the gain. Okay. So one way of increasing the gain of this particular amplifier is that you add another transistor M3 here. Okay. And I leave it as a homework assignment to calculate the impedance of this particular stage here. So instead of R02, whatever is the number that you get here, you can calculate easily and substitute and satisfy yourself that this resistance will be much larger than R01 here. So that's the direction to go if you want to build up even higher gain. But what will you lose in the process? What will you lose in the process? See, what you've done is you've increased the resistance at this particular node, right? So as you increase the resistance, what do you lose? What do you lose? 3 dB, right? The 3 dB frequency depends on the resistance at this particular node. Not only that, you've added one more transistor. That transistor will also add capacitances. You have to look at this particular node also, and that will also add some capacitances at this particular node here. So in general, what would happen is, yes, you can increase the gain, but you will end up compromising the 3 dB frequency as well. There's one more loss that you get here. One more drawback of this particular stage. One more drawback. So we have increased the gain. We know that 3 dB frequency will go down. What else is there? Output swing. Will that matter? See, earlier all you had to do was ensure that M2 was in saturation. Now what do you have to do? M2 and M3 both have to be in saturation region. And so there will be a drop from here to here, and there will be a drop from here to here. And therefore what would happen is the swing will get compromised. So you lose the swing here. So as you are increasing the gain, you lose the 3 dB frequency, you lose bandwidth, and you lose the swing as well. Okay, so that's the price that you end up paying. Okay. All right. So we're done with common source. Why should we go to common gate? What problem is common gate going to solve for us? What is the counterpart of common gate? Common base. What problem were we addressing in common base? Higher? Bandwidth due to what? What problem is bothering us that we want to go to this common gate amplifier? The Miller's effect is bothering us. The net capacitance at this particular node, input node, the CGD that is here is getting multiplied by the gain of this amplifier and is appearing as a large capacitance here. So what we are trying to do is find an amplifier which doesn't suffer from Miller's effect. And so why do we want another amplifier? Is basically this factor here. This is what is bothering us. The gate to drain capacitance gets multiplied by the gain of the amplifier. So note that as we build up larger and larger gain, this capacitance becomes larger and larger. So what we are looking for is a stage which doesn't suffer from this particular problem. And if you recall, how do we eliminate Miller's capacitance? Well, you're looking for a stage in which there's no capacitance between the input and the output port. Anytime you have a capacitance between input and output port, that capacitance will always get multiplied by the Miller's effect. So what you're looking for, a way to construct an amplifier such that there's no capacitance between the input and the output. And for that, so all these things are very similar to common base here. So for that, you're looking for, if you examine the MOS transistor here, what you note is that between the gate, if gate is the input and drain is the output, then of course CGD is there. Drain will always be at the output. So if source is the input and drain is the output, we note that there's no direct capacitance between source and drain. So the idea is that if you apply input to the source and you take output at the drain, then there's no capacitance between input and output port, and Miller's effect will be absent here. So that's the motivation for going to a common gate amplifier here, where you apply input at the source here and you take output at the gate. And of course, since you have to bias, so there's a bias voltage connected to the gate here. And so this is the configuration then. And as you can see here, if I build a small signal model here, this one will become small signal ground. This one will be ground here, and gate is our common terminal here. The input is being applied between the source side and the gate here, and the output is being taken from the drain side, and drain and ground is a small signal ground is also a gate. So that's a common gate amplifier, and analysis and all that are very straightforward. So I'm just going to give you the results. The voltage gain for this particular amplifier turns out to be GM plus GMB here, 1 plus GM plus GMB RS into RD here. Note an important point here, the gain doesn't have a negative sign. So it's a non-inverting amplifier, which was true for common base as well. And so these are straightforward calculations. So I'll not bother about it. R0 equal to RD here. And input resistance is what is very small. Now input is you're applying at the source, and when you look into the source here, you can easily show that the input resistance is given by this expression here. 1 plus RD by R0, GM plus GMB here. And RD by R0 is typically small. R0 is a larger, usually much larger quantity than RD. So this is small. So input resistance is primarily 1 by GM plus GMB. And this is a small resistance. As an example, if I take my transistor, bias it at 25 microamperes, GM is 100 microamperes, GMB is 42, and this number turns out to be around 7K. So it is small, but not as small as bipolar. In a bipolar, if you recall, we were biasing it at around a milliamperes or so, and resistance looking into the emitter was R pi by beta, which was around maybe 26 ohms. So it was really small here. So in this case, we call this resistance small in comparison to other resistors which are there. For example, RD may be 80K, R0 may be 4 mega ohm. So in comparison to that, this resistance that you see here, 7K, is a very small resistance here. All right. So the input resistance for this amplifier then is a problem. And you note that one of the major advantages of a MOS amplifier is that MOS offers you infinite input impedance. And now when you use a common gate amplifier, it's giving you an input impedance of only 7K. So that's a very negative feature about this common gate amplifier here. So if I compare common source and common gate for a moment, AV for a common source was minus GMRD, R0 was RD, and Rn was practically infinity here. AV for this is GM plus GMB, 1 plus GM plus GMB, RS, RD here. R0 is RD here. Rn is 1 by here. Okay. So if I compare the two, note that if Rs is small, the first term, this denominator is practically close to 1, and AV then is basically equal to GM plus GMB, RD. GMB is smaller than GM. So the gain of both of them are comparable. If you compare this and this particular term, if Rs is small, then the two gains are comparable. So common gate and common source give you comparable gain, provided Rs is small. If Rs is large, then of course the gain becomes very small. But for small RS, the gains are comparable. Output resistance is comparable. And input resistance are vastly different. So if I'm looking at both of them from the point of view of a voltage amplifier, common gate obviously is inferior. You know, it gives me the same gain, same output resistance, and very small input resistance, and therefore we see no advantage of common gate with respect to common source. In all aspects, it is an inferior stage as compared to a common source stage. Also, you can see if you take AV, R0 and Rn, you can multiply them together and you can get, if you recall, we had something similar for a common base. AV times multiplied by Rn by R0 is 1 for small values of Rs. So here, you know, if you increase gain, you are either compromising Rn or you're compromising R0 here. So unlike this particular stage, where Rn is always very, very large here. So obviously, as a voltage amplifier, it is inferior. Common gate with respect to common source. Its advantage, of course, is we know frequency response. All right. So frequency response. Let's quickly do this. So we have two nodes again, a node here and a node here. And as usual, one of the ways is we go ahead and replace the. See, I could have done this by open circuit time constant also, but let me for a moment put the small signal model here of the MOSFET. And so all the capacitors have been put. And if you look at this particular circuit, what you note is that I have to include now the source to body capacitance here. Source is here, and remember body will be connected to the most negative point, which is ground here. So body is connected to ground while source is no longer at ground. Okay. So normally source to body voltage, source to body capacitance was not coming into picture for common source, but for common gate, I have to put a source to body capacitance here. And CGS, of course, is over here. CGD is between these two nodes, and drain to body is between this one here. So if I look at this particular picture, I see that the CSB and CGS come in parallel. This is ground and this is ground here, so both of them are in parallel. And CGD and CDB are in parallel. So what I can do is I can simplify it to this particular circuit here. CGS plus CSB, we lump it here at this particular node, and CGD plus CDB, we lump it at this particular node. So we have this simplified circuit. Now we can apply our open circuit time constant approach here. So if I look at this particular node, which is the one that is being shown here, the net capacitance at this particular node now is CGS plus CSB. So that's here. The net resistance at this particular node, well, the net resistance at this particular node means you look down here, you see RS, and you look up here. When you look up, what you're seeing is you're looking into the source. And when you look into the source, you see a resistance 1 by GM plus GMB. Okay, this is what we had seen earlier. If you recall here, if you look into the source, you see a resistance 1 plus RD by R0 GM plus GMB here. R0 is much larger, so we neglect this. This is practically 1, and so the resistance looking into the source is 1 by GM plus GMB. So that's the result that we have used here. So resistance looking up here, 1 by GM plus GMB. Resistance looking down, which is RS. So that's the net resistance here. The other node is here at this particular one. Resistance looking up is RD. When you look down, you see a large resistance. When you look into the drain, you see a large resistance, so you ignore it. So the net resistance is RD here. The net capacitance at this particular node, this particular figure is showing you is CGD plus CDB here. So you put this here. So if you look at now the two time constants, if you compare this one versus this one, what you note is the capacitances are comparable. I have CGD plus CDB here. CDB, for example, is 4 femtofarad. CGD is, let's say, 0.4 femtofarad. So the whole thing is about 4.4 femtofarad. This one may be 4, and this one may also be around 4. So this is about 8. So this is about 8 femtofarad. This is about 4.4. The point is they are comparable. RD, on the other hand, is going to be 80K or 100K or something of that sort. And this is simply equal to 7K or so. 1 by GM plus GMB is around 7K. And if your RS is small, then it's even lower. Which tells us that this input time constant is very small. It's much smaller than this output time constant. And therefore, your 3 dB frequency can be approximated by only the output time constant, which is 1 by 2 pi RD CGD plus CDB. So the advantage that is coming now is that you can see that I don't have any, in 3 dB frequency, I don't have any Miller's effect here. I don't have any capacitance which is getting multiplied by the gain of my amplifier, because this time constant is very small, and none of the capacitors are getting multiplied by the gain part. So what we will have then is this particular amplifier then will give us a very high bandwidth. Okay, so that of course we know is the advantage of common base amplifier, common base and common gate amplifiers. I'll not go into the details here. The output swing is very similar, of this particular state, so I'm not going to. I'll skip that, and therefore now one can have a better comparison. We've already seen gain, input, and output resistance, the comparison between the two here. We know that this is a disadvantage here, but we know now this is an advantage. So the reason why we are even talking about a common gate amplifier is mainly because of this here. That this is an amplifier which offers you a large 3 dB frequency, much larger 3 dB frequency. So now all of you know now I can't use this as a voltage amplifier. Why? Because the input resistance is very small, so it's not useful for me. This of course is a widely used voltage amplifier, but suffers from a Miller's effect. So the idea is, can we combine both these stages together? Right? Can we combine both common source and common gate together? And we know that we can. Common emitter and common base, we knew how to combine them together. And what do we get? What do we get? Cascode stage here. All right. So this is something, simulation results which show the frequency response of common source 180 megahertz here. This is 411 megahertz here. Common gate is much better than common source here. The other thing is, so we know that we want to combine the advantages of both. The other thing is, if you look at this particular amplifier, common gate, it's a very poor voltage amplifier. Why? Because input resistance is very small. But we know that it's a very good, what kind of an amplifier? Current to voltage. So it's a very good transconductance amplifier. If your input is not a voltage, but if your input is a current. Now this amplifier has very small input resistance, which means what? This current will go predominantly into the amplifier, will flow into the amplifier, and you will get a voltage out. So it's a very good transconductance amplifier. This amplifier works well with current input, not with voltage input. Voltage inputs mean almost all the voltage will get dropped across RS and less will go into the amplifier itself. So the idea is you should look upon a common gate amplifier not as a voltage amplifier, but you should look upon as a transconductance amplifier. That if you have a current input, then the common gate amplifier will take this current. You can very easily calculate and show that if this is a small signal current IS here, this current will flow into the amplifier, will develop a voltage V0, which is nothing but IS times RD. So voltage output will be IS times simply RD here. So it's a very good current to voltage converter. Right? So that's the, and it's a high bandwidth amplifier. So good current to voltage converter, very high bandwidth, and that's the nature of this transconductance amplifier. You should look upon common gate as a transconductance, not as a voltage amplifier. So, how are we going to combine both of them? So we are looking upon common gate as a transconductance amplifier now, not as a voltage amplifier. And this, of course, is our normal common source amplifier. Now, if you think about it, this one, as I said, is a very good current to voltage. Can I say that this one is a very good voltage to current? Are you seeing that common source amplifier is a very good voltage to current converter? Voltage source into a current source. Okay, look at that. Say I take this amplifier, which is this one, right? This particular part here, common source stage here. If I build a small signal equivalent circuit, what will it look like at this point? Build a small signal equivalent circuit of this one. Will it look like this? At this node here? At this node, what does it look like? A current source, GM VGS. What is VGS? Nothing but V in and an R01. Is this a good current source or not? What is a good current source? It should have a high resistance. This is a very high resistance here. So you can look upon a common source stage as what? What did it do? You applied a voltage and it converted it into a current. So common source stage can be looked upon as a good voltage to current converter. So what you do is you apply a voltage, it makes it a good voltage to current converter. And which stage requires a current input? This one requires a current input. So what we do is we do a voltage to current conversion using common source, and we go from current to voltage using a common gate, and eventually by combining, what do we get? Voltage to voltage. Okay, so that's what we do here. We add this common gate stage here. Common gate stage here, and so this is converting. You can see here now this is I get a current source here, which is this current source here at this point here. Okay, instead of RS, what we have is R01. So all you need to do is take this out and put these two together into your common gate amplifier, and then you get a stage which is called a Cascode stage here. And so in the next lecture, we'll show you that the Cascode stage here has a gain which is same as common source amplifier. Exactly same as common source amplifier. Has input resistance which is very large because you're looking into the gate here, and has a frequency response which is superior to common source amplifier. So combines all the advantages of common source as well as common gate amplifier with one drawback. With one drawback. It's worse than this one and this one in one respect. And which is with respect to the swing. Because, you know, if you look at this one, all that I see is one transistor here, down. And if I take the output here, I will see two transistors down here. So I need to ensure that this is in saturation and this is in saturation. So swing is what you lose when you go from this or this to this particular stage. Otherwise, in terms of gain, bandwidth, it has very nice properties. Okay, so this is our Cascode amplifier. Now, as I said, I'll do the analysis later on. What I want, before you come to the next class, try this out. These are two, I'll show you two very useful results for MOS amplifier. One of them is the following. I have a MOS transistor. These are, by the way, all small signal circuits. I'm not showing the DC biasing circuit at all. Okay, so this is small signal circuit here. There's a voltage VG attached. There's an RS here. And what I'm asking is, build a Norton's equivalent at this node. Norton's equivalent at this node. Which means what? You'll get a Norton's current and you get a Norton's resistance here. And show, which means here, that when you look at this particular node, you can think of this whole circuit as nothing but a Norton's current and a Norton's resistance. You can always build a Norton's equivalent or a Thevenin's equivalent for any linear circuit, right? What I want you to show is that IN is equal to, given by this one expression here. And Rn that you see here is given by this expression. Norton's current is Gm times Vg here, divided by 1 plus Gm plus GMB Rs here. So that's the Norton's current, and Norton's resistance is R0, 1 plus Gm plus GMB Rs. Which means that when you are at this node, Norton's current is here and Norton's resistance. Okay, so that's a very, very useful result. Derive it and also memorize it, because we'll use it at lots of places. Okay, extremely useful result. The other one is, see, this one was at the drain node. The other one is at the source node. At the source node also, here also VG, there's an RD here. At the source node also, I can build a Norton's equivalent and show that the Norton's current is given by this expression. GMVG, 1 plus RD by R0. Rn is 1 plus RD by R0, Gm plus GMB. At this node. So these two results are extremely useful. In fact, you'll find in many of the subsequent analysis, if you remember this result and if you remember this result here, almost all the analysis becomes straightforward, just on the basis of these two results. Okay, so let's stop here.